So our modern life requires the use of batteries pretty much on a daily basis. Our cell phones, our laptops, our car keys, even our vehicles might have a battery if you have an electric vehicle. And if you use power from a solar panel or wind energy, the backup storage systems are often battery powered. Um, However, even though we use energy from batteries, some of us all day long, you might not know actually what's happening inside of a battery at the chemical and electrochemical level to provide that electricity that you're using. So in this video, I'm going to give you that explanation. I'm going to attempt to do it clearly, completely, in a way that connects directly to everything we've covered so far on the Tesla Institute. My name is Dr. Colleen Spiegel, and this is the Tesla Institute. So let me start with the simplest possible explanation using a AA or a AAA battery like this one that you can hold in your hand. A battery is a device that converts chemical energy into electrical energy through electrochemical reactions. So every battery has three essential components, and these are the same components that I reviewed in the fuel cell video. So we have an anode, a cathode, and electrolyte. So the anode is the negative terminal. There's, a little negative sign on your battery. That's where oxidation occurs and where electrons are released. The cathode is your positive terminal, so the plus side. This is where reduction occurs and where electrons are consumed. And then we also have the electrolyte. So this is a material that conducts ions between the anode and the cathode while blocking the flow of electrons. So in our standard AA battery, it's usually an alkaline battery, and the anode is zinc and the cathode is manganese dioxide. The electrolyte is potassium hydroxide solution. So here's what happens when you connect a battery to a circuit. At the zinc anode, the zinc atoms give up electrons. There's 2 electrons per zinc atom. And these electrons flow through the external circuit, through your device, doing useful work. At the same time, the zinc ions move into the electrolyte, and the manganese dioxide cathode, those electrons arrive from the external circuit to combine to form manganese oxide and hydroxide ions. So the electron flow through the external circuit from the anode to the cathode is the electric current that powers your device. So the same fuel cells work in the exact same manner. And so I spent a bit of time in that video reviewing the anode, cathode, and electrolyte system. So in your electrolytes, whether it's batteries or fuel cells, the ion flow through the electrolyte. It maintains a charge balance between the 2 electrodes, which actually sustains the chemical reaction. So when the zinc anode is consumed, basically when it's all been oxidized, the battery is dead. So this is most of our batteries. The chemical energy has been converted to electrical energy. The reaction cannot be reversed. And that means the battery is a single use. So at that point, a lot of times we just throw out our batteries. So these batteries, they generate direct current. The electrons flow in one direction only, from the negative terminal through the circuit to the positive terminal. It's constant, steady, one way, always. So this connects directly to what we covered in the AC versus DC series videos and why DC is the natural output of every electrochemical energy source. So let's go a little bit deeper because there are batteries that are rechargeable, right? Not all of them are single use. So this is the battery technology that's really transformed the clean energy world. It's definitely has been a step in the right direction. It's the lithium-ion batteries. And a lot of us older folks like myself, we remember when these came on the market. They really changed things because they made laptops lighter, be able to run longer. It actually helped make our cell phone technology possible and the way that it exists today. In the periodic table video, I introduced lithium, which is element 3. This is the lightest metal. It has a single valence electron. These properties make lithium electrochemically active and ideally suited for energy storage. So the lithium-ion battery works on the same fundamental principle as the alkaline battery. It has electrochemical reactions at two electrodes, the anode and the cathode, with the electrolyte conducting the ions between them. But there's one critical difference between this battery and our standard alkaline battery chemistries. The reactions are reversible. So during discharge, when the battery is powering a device, at the graphite anode, the lithium ions leave the anode and travel through the electrolyte to the cathode. And at the same time, the electrons flow from the external circuit from the anode to the cathode, generates the electrical current. And at the lithium metal oxide cathode, the lithium ions arrive from the electrolyte are incorporated actually into the cathode structure. So the electrons that are arriving from that external circuit complete the reaction. So when you charge your cell phone, when you plug it in, the external voltage actually reverses the process, and lithium ions are driven back from the cathode through the electrolyte to the anode, where they're stored in that graphite crystal structure. So electrons flow back through the external circuit in the opposite direction, driven by the charger, and that reversibility, that ability to store and release lithium ions hundreds or even thousands of times, is what makes our lithium-ion batteries so useful. So this is where the metallic bonding and band theory video content connects directly. In the metallic bonding video, I explained that lithium, like all alkaline metals, has a single loosely bound valence electron that it gives up very easily. And that same property that makes lithium an excellent conductor in a metal, that single free valence electron, is what makes it such an effective charge carrier in a battery. So the lithium ion that's stripped of its valence electron moves rapidly through the electrolyte, and the electron travels through the external circuit. Both processes happen simultaneously, and then your power is delivered. The electrolyte in a lithium-ion battery is a liquid solution of lithium salts in an organic solvents. And I mentioned this in the silicone solid-state battery video, that liquid electrolyte is both the enabler and the limitation of conventional lithium-ion technology. So this enables rapid ion transport, but it's flammable, and that flammability is the safety limitation that solid-state batteries are designed to solve. So let's connect batteries to the clean energy transition, because this is where everything we've covered so far on my new Tesla Institute channel comes together. In the AC versus DC video, I explained that every clean energy generation and storage technology produces or stores direct current. Solar panels generate DC through the photovoltaic effect. Fuel cells generate DC through electrochemical reactions. And batteries, which you hopefully now understand a little bit, store and release DC through reversible electrochemical reactions. So the clean energy future depends on batteries at a scale that we've never deployed before. So electric vehicles have a single EV battery pack that contains thousands of lithium-ion cells that are connected both in series and in parallel. So they deliver hundreds of volts at hundreds of kilowatt hours of energy. So the Tesla Model S battery pack, to name one example, contains about 7,000 to 8,000 individual lithium-ion cells. So grid scale storage, like solar farms and wind farms, generate power intermittently. The sun doesn't always shine, the wind doesn't always blow. So grid scale battery storage, and these systems can range from megawatt hours to gigawatt hours, stores that intermittent generation and releases it when the grid needs it. So this is what makes renewable energy grids 100% possible. So the next generation of batteries uses silicon anodes instead of graphite, and this stores nearly 10 times more lithium by weight, and solid electrolytes instead of liquid. And so this eliminates the flammability risk entirely. So batteries are not just a convenience technology. They're a critical infrastructure technology as fundamental to the clean energy futures as transformers were to Tesla's AC electrical grid. Nikola Tesla built the infrastructure that delivers electrical power to your home. Batteries are the infrastructure that'll store it, making renewable energy available on demand anywhere at any time. So this is the vision that Tesla was working toward, way ahead of his time. We're still building it. So a battery converts chemical energy to electrical energy through electrochemical reactions at two electrodes, and the anode and the cathode, with the electrolyte conducting ions between them. In an alkaline battery, the reaction is single use. In a lithium-ion battery, the reaction is reversible. The reaction is reversible actually hundreds or thousands of times. So it's really amazing. And in this next generation of solid state batteries with silicon anodes and solid electrolytes, the energy density and safety improvements could transform electric vehicles and grid storage in ways that we're only beginning to understand. So subscribe to the Tesla Institute for more energy, chemistry, physics, and engineering, all connected through the thread of energy that Nikola Tesla spent his life trying to harness for everyone. Nikola Tesla believed electricity should belong to everyone. We're still working towards that vision. My name is Dr. Colleen Spiegel, and I'll see you in the next video.